Hello. Can you hear me? I have a problem with the voice. Let me change the battery. Just a second. Okay, how's the audio?
Now it's better.
Okay, the audio is better now? Okay, I can't say I can hear you very well, but okay, let me share a presentation. Okay, so okay. Okay, are we ready to start? Are we waiting for anybody else to join? I see Rob, Matt, and I believe one of you is using the phone. Okay, did you get the link for the presentation? Actually, I can, I think it would be better if I share my desktop. Let me do this. I can't hear. Okay, can everybody hear me? Are we ready to start? Can you see my desktop? I don't seem to be able to hear you back.
Yeah, can you hear me?
I can hear you now, yes.
Okay.
Okay, so who am I speaking to?
This is Rob Pagini.
Oh, hi Rob. Are we,
How you doing?
I'm fine, how about you?
Good.
Are we ready to start? Are we waiting for more people?
No, we invited a number of people, but, they can join us if they want as we go, because I think we have a few of us on already.
Okay, so, it's me on this side. I don't know, I had a hardware failure, my camera just died, and we have audio only. Is that fine?
Yep.
I can go and find a new one, but I don't know what happened to it. I don't know if it's a hardware or software failure. Okay, so it's you. Who else is on the other side?
Cynthia, you on?
Can you?
I'm here, sorry.
Okay.
Hi, Cynthia.
Hi, Dave. How are you?
I'm fine. Okay, so, I've estimated about 2 hours. I think in the beginning we talked about three and I realized it might be too much for having people for 3 hours. Is that still okay? I mean, we can go through more examples. I can make it 3 hours if you want, but I suggest we start with 2 and then we continue.
That's fine.
That's fine?
Yep.
Okay, so let me start then. So today, we're going to have a 2-hour talk, as I said, about machine learning, trying to touch upon the several issues with machine learning, focusing mainly on, some general concepts. Basically what, assuming we have a company that is thinking about adopting machine learning, and they're trying to find out why they need it and how they can use it. What are the things that they have to consider, and what are the things that they need to know? Obviously, we cannot cover everything in 2 hours, but feel free to stop me and ask questions. And if you need, more clarification, or if you want to kind of extend more on that issue, I'll be very happy, to elaborate and talk more. The format of this presentation will be with slides, and occasionally I would stop the slides and I will go back to the whiteboard to explain things more in depth, or maybe answer questions. So there's 3 different parts of this presentation. The first one is called machine learning decisions, and there are some general concepts and what an executive needs to know about machine learning before embarking on that ship, before making the decision to adopt and put that in the operations of the company. The second one is more about understanding data. Machine learning understands numbers, but in reality we don't really have numbers. We have products, we have users, we have sales, we have documents. All these things somehow have to be crunched and converted to a representation that computers understand. And we'll talk about that briefly. And then the third part is algorithms. You're not going to see any mathematics about algorithms. I'm not going to present a full theory behind them. I would rather present a pictorial representation or explanation of how things work, and also trying to make a link with some real-world applications. So, in my mind, there's 4 to 5 reasons why somebody might want to invest in machine learning. The first one is to sell more, and I think that's what has attracted the attention of most executives. So, we have examples of banks trying to cross-sell products with credit cards and loan. So they have, big databases of data for different products, and there's a big opportunity for them to combine them and find new products, or customize maybe their products to their existing customers, and sell more. It's more like, I call this category pushing your customers to buy more for you. Marketing companies use that for targeted campaigns. I think we all know about the ad clicking business, the one that was introduced by Google. And in that category, I also put recommendation engines like Amazon and Netflix. Netflix not that much, because Netflix is trying to improve the customer experience, but Amazon is trying to make you buy more and more and more. The other category is reducing costs. For example, one of the companies I work with, Predictix, has a forecasting engine that helps big retailers like Walgreens to forecast better, so that they can keep in their stock less capital, which is very important for them. That increases the margins and makes them more competitive. And then there's another company that I'm working with called Predictor that they're trying to predict failures. So they're working with big paper mills and manufacturers where every time they have a downtime, it can cost them millions of dollars if it's not scheduled. Or even worse, a failure can lead to big damage that could cost even more. So helping them to predict these failures, again, reduces the cost. And in that category, we have the very famous example of, reducing fraud. So that also has to do with reducing the cost of operation, the operational cost. A credit card company, a bank, an online auctions company like eBay, it's very important. Now, I call this, it's not really a hard rule, but most of the methods used in this kind of business are supervised. And I don't know if anybody has heard the term supervised learning before. Are you familiar with that term? We're going to talk about that later, but I'm just trying to sense also, because I don't really know the audience about the level of expertise. So is anybody in the audience who doesn't know what supervised learning means, for example? Feel free.
I don't.
Don't be shy. So supervised learning means that you have a teacher. You are learning something. So somebody is giving you data and also gives you labels. Okay, it tells you that this transaction that happened on this particular day by this particular person, gender, location, blah blah blah, was legitimate or fraudulent. So when you're teaching a machine, you're providing information. There is also some other. The other kind of like part of machine learning is called the unsupervised, where basically you give the data to a machine and the machine figures out what is good and what is bad, or kind of like split that into clusters. And there is something in between which is called semi-supervised, which means that I give you data and some of them are labeled and some of them are unlabeled. And you use all of them to come up with decisions. So we don't have to really emphasize about that at this point. We'll talk about that later. Now, the other two business cases that I've seen is drive the development of products. And when I say drive the development, I mean either come up with new products, completely new ones, or improve the ones that you already have. So, for example, there are companies like 3M, and I'm also affiliated with a lab here at Georgia Tech that I help them use data science to invent new materials. So basically, we're trying to synthesize and make a new material that has some specific features, conductivity, elasticity, and so on. You might have heard about pharmaceutical companies trying to design new drugs. Okay, so basically they have models about proteins and molecules, and they're trying to sort of like find all possible combinations. That ideally you would like to test all possible combinations and see which ones are giving you the best performance or the desired specifications. In reality, we know that this is impossible to try all possible combinations, and that's where machine learning is helping you to try the combinations that they are most likely to meet your requirements. And when I talk about improving user experience, we all know about Apple and Google and how they design their websites and their products, where basically they're using A/B testing. And for those of you that don't know what A/B testing is, basically they will take the website and then they will make a permutation of the features. So they will have a website with blue, green, yellow colors, different colors. They will put them in production and they will see which one attracts more clicks. And that is not as easy as I described it, because you have to somehow sample your population so that you make decisions that are statistically correct. And not only that, Apple, for example, collects all the user experience or user behavior on iPods and iPads, and Google does the same. And they're trying to find things that people are trying to do and they're failing, or things that people are trying to do and they never thought about it. Okay, so for example, I remember when I was working at Google the days that Google Docs came out, they realized that people were using Google Docs to store pictures and share pictures with them. So they decided to, I think, I'm not sure if they had Picasa at this point. I think they did have Picasa, but not on the web. So, they pushed Picasa more, and they tried to educate their customers that, this is the right way to do it. And that's kind of like a simple example, but this will involve machine learning. But there's more advanced ones. For example, when you talk about clickstream analysis, trying to find out what is the path that people are using when they are navigating on a website. And the last category is try to solve a problem that you had no idea how to solve it before. Okay? And for example, finding terrorists. There are organizations that they came, okay, we knew the problem before, there were some approaches kind of like very limited, and now with the advances of technology and especially in graph theory, there are companies like Palantir that they have created software that utilizes machine learning, which is trying to effectively find terrorist networks. Or you want to make a robot, making a robot thinking and walking and navigating independently, that is completely based on machine learning. There's one company that I've worked with called Bambara, that they make software for detecting botnets. That was a problem. Nothing existed before. It's becoming increasingly more and more necessary to have protection against botnets. I don't know if any of you saw the reports yesterday about this huge botnet that attacks WordPress websites. So they use 100,000 machines to try common passwords and taking ownership of blogs. So a problem like that couldn't really be solved before with traditional techniques, and with advances of machine learning, we're able actually to detect this kind of botnets. And of course, in medicine, except for the drug design that they talked about before, there are problems about finding the impact of a drug by using it with another one. So they have this problem, like when they do clinical trials, they can find the effect of a drug only if you're taking just that, and maybe a few others that they suspect we can take. Now there are companies that they are mining the prescriptions from CVS and Walgreens massively, and they can figure out if there are side effects by using two drugs at the same time. And not only that, they even realize that sometimes by taking a drug that is completely unrelated, or we never thought about an effect on a common disease, they can find out that it can actually help. And why is that? Because they have a lot of data, they can mine them, and they can find, for example, I don't remember the specific case, but I think it was with Tylenol or another one very common, like over-the-counter drug, that they realized it was helping people with a specific disease. So typically, this kind of approaches use supervised learning. Of course, I don't want to make some hard claims. Mostly they're using mostly supervised. Sometimes we use supervised too. But that's not really. That's like a minor detail. We don't really have to stand on that for too far. And these two problem categories belong to what we call knowledge discovery. Okay, so we know maybe a few things or nothing, and we're trying to use machine learning to discover new knowledge. Are we okay so far? Are there any questions? I assume not. So, okay. So the next thing is, whenever you decided that your organization is going to use machine learning to solve, the problem that you are having, and you have to make a decision. Basically, you either have to have a classification engine or a regression engine, prediction as they call it. So let me introduce the notion of classification. Classification is what you really understand in your everyday life. I'm given something and I have to decide whether this is good or bad, black or white, A or B. The regression or prediction, as we call it, is trying to predict a value. You know, if I do X, Y, and Z, what is my weight is going to be? Okay, for example, I just remind me of some companies that they do software for helping people to exercise and lose weight. So we are trying to make a prediction. If the weather is such and there is a promotion on this product, how many units it's going to sell. So this is a prediction or regression problem. So basically, if you're trying to decide between 2 or 3 or maybe a few discrete variables, decisions or labels, you call that classification. If you're trying to predict a continuous value from 0 to 100, for example, from 0 to 1,000, this is called regression. Okay, is everybody good with that? I think that's probably an easy concept. So consider the following problems. Your company is trying to find, so you have a database of books. Let's say you're a publisher or a bookseller, and you're trying to find which books are really similar. Or you're having movies like Netflix. You're trying to find which movies kind of like the same. Or you have a company that has images like Flickr, and you're trying to find which images are similar. Or you're trying to find which users or customers are kind of like on the same category. Or you're trying to predict a rating. I mean, what do you think how many stars do you think this customer is going to give to this restaurant or to this book? So whatever a customer can pick, okay? There's 2 ways that we can model a problem like that. The one is called behavioral modeling, and the other is called content modeling. So let's see what these 2 things are. So the behavioral modeling doesn't really look at the content at all. It looks at the customer, at the agent, as we call it. So, for example, when you have a bookstore that you have customers buying books, you look what every customer bought, and you associate customers based on the common things that they have bought. So 2 things are similar by association. Okay, or if you have a movie, you tend to classify assimilate users by the movies that they have, the common movies that they have watched or liked. Or you're assuming that 2 people are going to become friends because they have a lot of common friends. Or you assume, in Pandora, for example, that 2 people are going to like the same song according to the likes that they've given to other songs. This is also something that you might have heard with the term collaborative filtering, and it turns out to be a very successful strategy. So you don't really know what is the feature of the book that makes 2 users like it. You don't really know, it doesn't really give you any explanation about the content. Okay, so if you're trying to make recommendations for somebody, you're not really looking at the content. You don't have any idea that this person liked that book because of the author, or maybe he liked that book because of some particular chapter or the plot or anything. So you don't look at the content at all. But you just kind of see his social behavior, and you infer from that what he's going to or she is going to like. Do you feel like you understand the concept? Have you heard that before? Is there anybody who wants to spend more time on that? Okay. I assume, and unfortunately with WebEx you can't really see. Okay, we have the chat over here. If you need to interrupt me and for some reason there's an audio problem, feel free to interrupt me from the chat, okay? So I'm also writing, feel free to interrupt from the chat box. Okay. Now that we described the behavioral modeling, let's go to the content modeling. So if I wanted to find out if 2 books are the same, I could probably make for every book extract some features like the keywords, some key phrases, the name of the author, and any other, maybe the publisher, maybe the cover of the book, maybe the images, and trying to find, if 2 books are the same, based on some features that they have to do with the context. The same thing with the movie. So here I would associate two items based on their content. And I would be like a classifier that will tell me, given this and this, are these, or a similarity function that will tell me that are these two the same, or are these likely to be the same, and I would get an answer. Now, which one is better? It turns out that behavioral modeling tends to give better results. It's also very easy to implement because it kind of goes like ping pong. Okay, Nick has a lot of common books with Rob. Rob also has some common book with Cynthia, so we associate that probably Nick and Cynthia are going to be, also similar. So it kind of like builds a network by taking two people or two users, two users that are very, very common, close to being the same by the items that they have purchased or used or liked. And then obviously, so as I said, user 1 would be very similar with user 2, and then user 2 will also be very similar with user 3, with user 4. So it makes kind of like a network, and it starts connecting the dots. And that works pretty well. And it scales also. It's very easy to scale with millions of customers and millions of products, even billions these days. And we have, as I said, great cases with Amazon, Netflix. Google News, I think, was the pioneering. It was the first one that used this type of technique, and Pandora. But there is a problem with that. So you are a company, and you decide tomorrow. So let's say you're any company that sells products. Let's say you have a portfolio of 10,000 products, and you have, let's say, 100,000 customers. Does anybody see a problem with this approach? That if you implement that, there is a case where you are not going to be able to make a recommendation or say, this user is similar to the other. Do we have any guesses from the audience? A case where that wouldn't really work. Think about your organization. For example, let's say about Comrise. In Comrise, you have candidates, and you have the resumes, and from resumes you can see which companies that worked before. So you can say that, because these two people have worked in the same type of companies or same companies, then next time I'm going to recommend a candidate to a client. If I pick Nick, then I also recommend John, because from my machine learning engine I can infer that Nick and John are the same. So can you see a problem over there? I challenge Rob to tell me what's the problem that you would have by following a technique like that. And I can help a little bit. So what would you do? Does Rob or Cynthia have any idea of that?
Are you just using the companies that work for, or using other
I can't hear you very well.
I'll pick up. Are you just using, companies they worked for, or are you using other attributes like education or skills, things like that?
Let's say for simplicity right now that you're using only the companies that worked before. Okay. So there's going to be
that could be one.
Yeah, there can be a problem with what are you going to do with students that just graduated and that never worked before. Okay, this is going to be a problem for you. You won't be able. So this is kind of like called the cold start problems. Okay, you have SKUs. You have some products in your company that you're selling, and you can say that this product is similar to that because it has sold to the same customers. So what happens when you have a new product, like a new product is coming to the market, and you have no history about that. Nobody has bought this from your website. Or you have a new customer that has bought nothing before from your website. Okay? Do we get that idea? So there are problems that you might not really have any history. Okay, so you might have a problem like that where you have no history. What do you do? For example, let me give you an idea. Here at Predictix, they have this problem that when they have a new product that they won't have historical sales, they cannot really put it on their forecasting engine because their forecasting engine is based on the historical sales. So in that case, as I think you started saying, Rob, you need to find other attributes that make them similar. For example, in what college they went, what they studied. This is not behavioral modeling, this is content. This is characteristic that characterizes the candidate. It doesn't really characterize the user behavior. So for you as Comrise, the user behavior is where it worked before. And the content is, their education and their interests and their classes they've taken. So in that case, where we have no history, no behavioral history of the user, we use the content. For example, with Pandora, when they have a new song, they analyze the tempo and about 100 different other, if it has electric guitar, if it's rock, pop. So they have people listen. They do that manually. They listen to the songs and they create features that have to do only with the content. Okay, and based on that, they find similar songs, so they try playing them together, and by the time they put them on a playlist, within hours they have likes and not likes from users, and based on that, now they can put them in lists based on their behavioral, activity. And the problem with content modeling, why it doesn't work and why it's hard, is that you don't really know by default why people that listen to Andrea Bocelli also like Madonna. In terms of content and features, instruments and tempo and whatever other things they can pitch and the two items have. You can't really make any decisions, okay? It's the human nature. It's probably something deeper. We don't really know how brains work and why we pick these songs together. Music is probably the best example because when you make a playlist, you put songs together that they're not necessarily the same. Actually, it's very boring if you listen to the songs that they're very, very similar in terms of melody and songs and lyrics and things like that. If you listen to an hour of radio, there is a big diversity. Why we put these things together, we don't know. But based on that, we can make, recommendations or playlists. So I believe if you go back, each of you, into your domain, let's say to candidates for Comrise, you say, I don't really understand why people that they work for this company then go to another company. Maybe it's because there's a historical culture between them, or we know, for example, that people that work for software companies, they go to consulting companies maybe later to make more money because these companies want that particular skill. But we've seen examples where people transition from one to the other, and as an expert, you don't know why it's happening. And even if you can explain that as an expert, it doesn't really scale to have one expert reviewing all these things. You want to do things automatically. Which comes to kind of like my next point. Machine learning doesn't always perform, we don't want machine learning because it always performs better than the expert. Sometimes we want machine learning because it can automate the expert. Okay, even if it does a little bit less in terms of performance compared to an expert, we will still prefer machine learning because it can scale. Okay, so bottom line, behavioral modeling tends to work the best because it captures non-linearities and correlation between the data that content modeling cannot capture. Of course, this thing is changing by the use of a new technology called deep belief networks. Do you remember a few months ago maybe more than a few months, it's almost about a year ago, when Google announced this experiment they did where they took about 1 million frames from YouTube, they put it into this kind of like magic technology called deep belief networks, and eventually this thing did some magic, and it grouped some pictures together, some images together. When they went back and they looked at these images, they realized that these images were cats, the animals. So apparently the algorithm on its own, that's an example of unsupervised learning, they didn't provide any information to the algorithm. Realized that these particular images, they have this specific, correlation together, and it wasn't really just a cat photographed from different directions. No, it was all sorts of cats, different colors in different environments, and this is one of the cutting-edge research in machine learning, and probably the next wave of machine learning, which we're going to see commercialized in a few years. I can't really predict. I'm very bad with predictions. So content modeling for the moment it can augment things, but it tends to behave worse than behavioral modeling. So, are we good so far? I see some more people just joined. Okay. Now, let's talk about two other concepts. So far, we've seen different taxonomies of machine learning. We talked about like supervised and unsupervised. We talked about behavioral, contextual modeling, content modeling. I don't think contextual is the right. I prefer the term content modeling. And then there's something called generative vs. discriminative. So I'm not expecting for you to know about this, and I'll try to explain it as simple as I can. Discriminative modeling has to do with the fact that they are giving you two different classes of products or points. In machine learning, every item corresponds to something we call a point. We'll see that later. So they give you two sets of items, and you have to classify them. One way to build a model is by describing the features very well, the features that one item set has, and another set of another set of features that the other has. Okay, so for example, if I was giving you apples and oranges, you will say, I will pick my feature as the color, and I know very well that if I ask only one question, if you give me a fruit and I ask you, is the color orange or not? If you say orange, you will say, okay, I know this is the orange fruit. Or if not, it's an apple. So there's a very well discriminative feature over there that is just enough to discriminate them. So by just taking the color as a feature, I can tell if it's an apple or an orange. Now, imagine the case that we have several types of apples and oranges, and some of them, for example, we have a certain type of orange that it's really, really close to red. Okay? So that feature in its own, the color in its own, wouldn't be able to discriminate. Or it would discriminate the two sets most of the time, but there are going to be some times that it wouldn't. So in that particular case, we have to add an extra feature and say, if it's not very orange, so it's closer to red, then I have to ask an extra question. In that case, I'm trying to be more, I'm trying to use extra feature or extra complexity to discriminate between them. And I'll stop at this point and I'll give you an example on the whiteboard, just to understand. So, let's say that I have this class of objects here. Can everybody see the whiteboard? In this particular case, if I just draw a line, I can say that this is class A and this is class B. Okay? Now, it means that, the features are good enough, are very good enough that I picked, that they can really discriminate. Now, let's revisit that case. So X's and O's are different classes. In this particular case, my separation surface is something like this. It's something more complex. Okay? So the difference between this and this is that here I have invested a lot of time trying to make, a decision. So this is a more complex line, okay? You can see that this is just a straight line. This one has curves. The more curves your line has, the more complicated or complex your model is. It means that's like a harder problem. And it kind of like tells you that when you are in this domain, if you're a query point, you're asking, okay, I have a new point over here. Is it A or B? It's definitely here it's A because it's on this side of the surface. Everything that's on this side of the surface, it's A, and everything that is on this side, it's B. Okay? Now, if you're if you're over here and you're asking question, if I have a point over here, or over there, what it is, you can probably, sorry, just a second. No. You can probably say, okay, I'm just looking at let's say that this is the y-axis, and this is the x-axis. I can make a very easy decision. I just look if it's less than 0. Okay, I know that it's A. Now, as we're approaching and we're getting closer to this line, you have to ask more questions, and you have to do, as you approach this line, you need to use more discriminative power. You say, okay, the closer you are here, the more complicated your model has to be in order to make the right decision. But when you visit that, is that clear to you, the difference between, generative modeling? It means that my features are so good that with a very simple decision boundary, I can, I can be correct. This is kind of like, of course, there is a more mathematical and rigorous way to define discriminative versus generative. But let's stay with this for the moment. Okay, so we go back to the slides. Now, which one is the best? It turns out that if your generative modeling works, so if you take a problem and you model it in a generative way, which means that you pick some features so that a very, very simple classifier can have very good performance, it means that you've done a very, very, very good modeling of your problem. You really, really picked features that they are unique and they identify each class perfectly. Now, if you model something, if your features don't work very well and you have a lot of, mistakes in your classification, so something is A but your classifier says it's B, it means that you have to invest more time discriminating between your classes. It means that your features are not really perfect because they create confusion, and you have to be really, really clever on the way you're making your decision. In general, discriminative discriminative, methods tend to train well, but sometimes they have this problem of overfitting. And I'll go back to the whiteboard. So, in this particular example over here, A from B is very far away. So, if a new point here, comes here, or here, or here, we're very confident it belongs to class A. The same for class B. There is a big, as we call it in machine learning, it generalizes better. So anything new, a little bit far away from your training examples, will be correct. Now, of course, if something is close to the boundary, very close to the boundary, you're very prone to make mistakes because you really assume that this is a boundary, but what if the boundary was making a wave over here? Now, on the opposite, in the discriminative models, you have, more chances to be wrong on this curve. Now, there are problems, and I'll just say that and continue because it might really get boring talking more about that. There are problems where your generative modeling really captures some basic assumptions of the model that make it work really well. For example, in fraud, where I've worked before, internet fraud, there's a specific behavior that thieves or bad guys will always adopt and good guys will never do it. Okay? So, in this particular case, the generative modeling will work very well. So, for example, the cyber criminals, they tend to register domain names and take them down very quickly. So they register only for a few hours and then they withdraw them because they want to be agile. They don't really want to be identified. While a legitimate user like Comrise has registered the same domain for many years. Okay, so this is, for example, a good feature that if you pick, it's not just that. I'm just giving you a very naive and simplified version. I'm hearing a noise. Has everybody muted? Okay, this
put us on hold and we're getting music.
Excuse me?
They put us on hold and we're just getting their music.
Oh, how did I put you? Okay, let me fix that. Yeah, I'm hearing that music too.
Everybody,
why does it have?
take you off hold.
So,
Nick, can you ask? Can you chat everybody and just ask them to take their phones off hold?
So be caller user 6. You see the microphone there with the noise coming out?
Yeah. I see user 3 and user 6 probably. I can. So somebody. Okay. Let me fix it. Okay, so it's the user number 6 who put us on hold. That's why we're listening to the music. Is that right?
Yeah, it looks like they've put us on mute now and we're okay.
Okay. It's user number 6. I don't want to mute you. I think if I mute you, you can unmute yourself, possibly, okay? Because if anybody wants to ask a question, I don't want people to feel restricted, okay? Okay, great. So I was talking before about this particular, case about fraud, where there are some features you can pick And these features tend to work very well just because structurally, the bad guy cannot behave like a good guy, cannot pretend to be a good guy, because if he pretends to be a good guy, then he was going to be caught. Now, for those of you that know me well, I have a particular thing about books, and probably the best and more pleasant way to learn about machine learning, since, you're not experts. I believe you're very busy people. You have a lot of things. You have to run your organizations. You have deliverables. And I believe most of you don't really have the luxury to go and attend the Coursera or Udacity course. For those of you that don't know, if you really want to learn machine learning properly, educate yourself, understand the concepts, there's the following option. One is the Coursera. Coursera offers like 3 or 4. There's one general one, another 3 or 4 more specialized machine learning courses. Udacity has also a very good one, maybe more than one. If you are more like advanced, you might want to take the machine learning certificate from Stanford. It's kind of like on the graduate level, and I highly recommend that. It's a little bit expensive. And there is also some other, like Caltech has a series of talks. The NYU, very good course on big data machine learning from 2 of the pioneers, John Langford and Jan LeCun. Jan LeCun was one of the winners of the Netflix competition. But if you don't have the time, I highly recommend that you kind of like motivate your employees to do that. Maybe I know that some companies are giving bonuses to employees that bring them back certificates from Coursera. They pay them something like $4,000 or $5,000 if they manage to fill out the course. So as we said, you don't really fall in that category. So you probably travel a lot, and the best way to learn about machine learning is through some books. So the best one, if you had to pick one of these 4, is the Super Crunchers, the red one. They kind of like goes through case studies, trying to prove how machine learning has been successfully applied to different types of the industry. And it's easy to read because it goes case by case. And surprisingly, it was written by a lawyer who at some point realized the power of data and focused on that. The next one is smaller. It's more about understanding the concepts of probability in real life, and something we're going to talk about, the naive Bayes classifier and how you're thinking. So Bayesianism is kind of like, we're not going to talk much about it, but it's a trend in machine learning, and it's a way of modeling things. The other one, you might have seen it on New York Times. There's a lot of buzz around this book, kind of like say why so many predictions fail. And the third one is, again, an interesting, easy to read book about machine learning and how kind of like the very basic form of machine learning helped the British beat Enigma. It has some really, really nice examples and historical facts about successful use of machine learning. And going back to the yellow book, I've used the term prediction, but I just want to make clear something clear about machine learning. I don't really like the term prediction. Prediction means that you're trying to find out something you don't know, you haven't really seen before. That's not the case with machine learning. Machine learning, I think the best word to use for prediction machine learning is called planning. So machine learning is trying to predict based on historical data. So for example, I'll mention again, predictics. Predictics is trying to forecast the demand of products based on historical information. Okay, if an earthquake happens, or if all of a sudden the economy goes down, you might have heard of this thing as a black swan, or if a new effect comes in, all of a sudden something became digital and the physical doesn't sell anymore. All these things cannot really be predicted. So when we talk about prediction in machine learning, we're talking really about planning. You're trying to make a decision based on things that you've seen before, patterns that you've seen before. Now, somebody might say, so you talked about knowledge discovery before. You talked about discovering botnets that you haven't seen before. What is this about? That is true. We discover things we haven't really seen before, but we have seen similar behavior. So we're making an assumption about our model. Okay, we're making assumptions. We know, for example, how proteins work. We know how, materials behave. We're making some, we're doing some general principles, and based on these general principles, we're trying to see what else can happen. For those of you who come from an economics background, it's more like a simulation thing, where you say, okay, these are the policies, these are how, the economical agents act, based on their data. Throw a billion or a million, actors in your model and try to find out where the economy is going. So for those of you who are, familiar with simulation, machine learning looks like simulation. It's just like more clever, and it has much more information embedded in it. I don't want to open a discussion about the difference between simulation and machine learning, but they are cousins. They are related. So now we're moving to the second part of our presentation, which we're actually going to go a little bit fast, representing your data. So we'll see some common data problems. We'll talk about representation models. And the storage model starts a little bit more technical. I'm not talking about whether you store them in Hadoop or SQL Server or things like that, but it has to do with representation on the register of your machine. Very, very brief introduction about algorithms for sparse and dense data, and then the next part is really about algorithms. So the data scientist, probably one of the most well-paid jobs right now, and the hottest, and the one that companies that come right are really looking to place for their clients. So this kind of describes, you might not really understand all the words, probably most of them, but a typical question for a data scientist will be, can you please run k-means ++ with k equals 4? Can you please run a Gaussian support vector machine with these parameters? Can you tell me what are the 3 first eigenvalues of the covariance matrix? Can you run spectral partitioning on the graph? So these are the questions that the data scientist would love to hear from his or her boss, because this is the language that they understand. Okay, data scientists understand math. Most of the time they won't understand business, and maybe they won't understand even the domain model. These are the things that they know when they come out of college, and they will be thrilled if you were asking them this question. Chances are that you're not really going to ask them these questions, okay? Because you don't really know what is k-means ++, you don't really know what's the Gaussian SVM, you don't know what's spectral partitioning. Okay, so what do we do for that? There's obviously a communication gap between what they know and what you know as domain experts and business people. So the reality of the set is very different. First of all, we have to see, I'm going to present over here, how we map all these different types of data into numbers. So text data, I believe that's called resumes in Comrise's world, user preferences, web clicks, IP traffic, social network relationship data, market basket data, sales volume data, other type of descriptive data, images and video. This is probably most of the data that you see in everyday life. Some of them are most common than others. So we have to find a way of, first of all, translating this before we're going to ask the questions that I presented before. We have to ask the question, okay, here's an organization, here's the data I have, how I convert them to something that the computer understands. Okay, so the most common or the best way to think of data is graphs. Again, some of you might have an engineering background, some of you not. But I'm trying to explain what is a bipartite graph. Okay. So, I think we have a pointer over here or not. Okay. So, on the left column over here, we have users. So, A, B, and C are users. And C, X, Y, and Z are movies. So every user is a node, and maybe we can use a different color over here. No. And every movie is a node. Notice that this graph is sort of divided into two sets of nodes. Okay, there is no direct link between A and B. Okay, edges. This thing is called an edge. For those of you that don't know, edges go. So edges go from left to right only, or right to left, but not from left to left. Okay, so let's say that W, X, Y, Z, as I said, are movies. You see, in this particular case, we have the complete graph, which means that A has seen all movies, B has seen all movies, C has seen all movies. These edges can have a weight, which means that A saw movie W, but gave rating as 1. B gave X rating number 4. So all these edges are not really equivalent. Okay? And this can be, user books. This can be a document, A can be a document, and this can be the words that the document contains. And the edge can represent how many times, this can be like number 3. Like that A contains word W 3 times. Okay? So, and again, if I wanted to find out how similar A and B are, I would have to go to W, do and bounds to B. So you see over here that there are several paths, connecting A and B. We'll talk more about that later. Now, still, computers don't understand this is an image. They can understand that. Okay? But they can understand this. This is a matrix. A matrix is nothing more, like the normal table, where here we have, as I said, users, and here we have movies. And this number over here tells me that this particular user is connected to this particular movie, and this is the rating. Are we okay so far? I don't really see any problem. If you see any problem, okay, here are the colors. I didn't see that. Okay, so I gave you just a few examples, but this is the way that you should think about data. Okay, again, one side is the point that interests me, like user and the movie, the word, this could also be some other features, like this can be the height, the weight, the color of the eyes, okay? And the edge is the value that, like, Nick is 6'3". Okay. Sorry, good enough. Again, let's annotate. Nick, sorry. I keep having this problem with. Can't go back. Maybe I'm going back over here. Nick and 6'3" over here, and this could be 200 pounds, and blue, Now there's a question, how do we put this blue on this matrix over here? Because the matrix doesn't understand, letters. It understands only numbers. So we're going to see that later, how we convert that. Again, if you feel like this section is too technical for you, we can skip it, okay? Now, again, I would really appreciate feedback because I have no idea about the audience and how diverse it is, and probably there are people that they find these things boring, and maybe other people that they find these things, too difficult. I don't know. Now, as I said before, if we try to find relationship between the items that we're interested in, like if we want to find, how A is connected to B, we go from A to W, and then, from W to B. Basically, I took this graph and I mirrored it and I put it over here. So now you can have a relationship between, B and C, or C and D, because this relationship might actually not be symmetric. So now it's very interesting. Now we're talking about relational data. Okay, we started with some absolute representation, which is, user to movies or document to text, and now we're going something like relationship between text, documents, relationship between users, relationship between books, relationship between images. Okay. Now, let's have another example. Again, my favorite example about supermarkets, something everybody understands. Today, volume, it's something that depends, so how much you're going to sell today depends on how much you sold yesterday. It turns out it's very relevant to the temperature or the weather, the humidity, where you put the product, is it a holiday or not? I mean, you get the idea. Now, so again, this is a problem where you're trying to predict a numerical value versus some other numerical or categorical, like the is holiday, the categorical value, yes or no, okay? So if you had a supermarket and you're trying to make predictions about how much you're going to order every week, that's something you would use. Now, let's see how we convert documents, and I kind of hinted at before, into numbers. Okay, so imagine that this is your first document. John likes to watch movie, Mary likes to. Say, John also likes to watch football games. We're going to use something that people call bag of words. This is the most typical representation for what we call unstructured data. And again, structured data are the data you have in your database. Name, address, age, education, courses, blah, blah, blah. This is normalized, this in columns. You know that your data has, 1 million entries and 10 rows and 10 columns. But in reality, when the Comrise receives resumes, this is unstructured data, and they either have to kind of extract the information manually or with some NLPs, and still, most of them, it's not really, I will call them semi-structured data because they kind of have some very common key terms like education, previous employers, and things like that. But if you take newspapers or scientific publications, they don't really have a structure. So basically, in order to start analyzing, what you're doing is you're taking all the words and literally throw them inside the bag to remove the order. And that's the same thing we'll do with images, how you're going to see later on. Let's see how we do it. First, we'll do the dictionary. We will say that, John is word number 1. Likes is the word number 2. 2 is the word number 3. So you basically make a dictionary out of all these words. Now, Then what you do is that you take, this first document, you count how many times does it have the word zone? 1. You put in 1 here. How many does it have the word likes? The word likes is, appears there twice. 1 here, 1 here. So I'm going to put a 2 over there. Okay? So some words like football doesn't appear, so you get a 0, and so on. So let's take a simpler case. So this is how you took text and you converted that into a vector of numbers, okay? And then that's kind of like another case where the document ones I like databases, the other ones I hate databases, and again you do the mapping from here to there. Now, if you take something called the dot product between these two vectors, it gives you the common, how similar these things are, the number of common words. We can use buzzword words for, different types of data as images. So for example, you take an image, as you see over here, and you split it into blocks. So if your image was something like that, you will take blocks, and then you will start taking these blocks and putting them into a bag. That's why I have this picture over here, a bag of words. That's another way. So again, this was a bicycle, you split it into pieces, you threw it over there. Now, the next thing is that you collect all these blocks, you collect them, and you throw them into this, and you make a dictionary, so you find the most common ones, the ones that repeat, all of them. And then, so you made let's say that this is your dictionary over here, the same way we did it before. And these are here they are. These are like the most common blocks, or common, like, sometimes they call them the visual words. Okay? Excuse me, I don't know if you see also the WebEx blocks, if they're blocking you. I just realized that you might be seeing them. Anyway. And basically then you see how many times you see that this particular block that we see over here appears several times on this particular visual document. So what you achieved over here, and this is one of the most successful techniques in image processing. Instead of trying to detect a nose or an eye or blah, 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 that's what Google does most of the times to find similar images. Because they have such a big volume, they split it into small blocks, and they're trying to find the most common ones and make visual dictionaries. That was kind of one of the preliminary steps that the guys at Google used in this experiment with trying to identify cats in YouTube. This is something that they went through. It's probably obviously not the only step, but it's definitely one of the things they do. Again, we sort of talked about that before, but doesn't really hurt to repeat. With Netflix, the Netflix data set was 500, these are statistics, 500, over 500,000 users, 18,000 movies. If I've rated the movie, I put the rating here. If I haven't, I put a 0. Okay? Many questions so far? Are we going too fast? Too slow? Again, an IP traffic network, you measure the traffic that left from this machine to this machine. So basically it's machine 1, machine 2, machine 3, machine 1, machine 2, machine 3. You represent that with a matrix. Okay. These are the descriptive data that I talked before. Job, Nick, Peter, age, income, total purchases, hair color. So far, we've seen how we can convert any type of data to basically a rectangular of numbers. I think we're kind of like getting close. It's 2:15. We have about 45 minutes. We'll spend more time on the algorithms. So the storage model is either you store that with key value. So for example, if you have a visual dictionary of 20,000 images, you wouldn't really store them as, and most of them are zero, you wouldn't really store them as something like this, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, because you have a lot of zeros like that. Okay, so you prefer, okay, let's skip. You prefer, as I call the rectangular grid. So you store, you have a zero value, a key value storage model. You only store the non-zero values. Now, this is the case that works most of the time. When you have descriptive data where you basically have only 10, 20 attributes, you should use a continuous grid, your rectangular grid. So you store one value after the other. You don't really store the key. The reason why I'm emphasizing about that, because this is, in case we have engineers in the audience, this is one of the most common problems why your machine learning algorithm might run very slow. Because you say, okay, with key value I can store everything, but if your data is really contiguous, so it has like only 10 values and you use key value store, then you can actually end up with horrible performance. I know it might sound naive. I've seen, projects failing just because of that. Now, the reason why you want to use dense data is because they are specialized library. I'm not going to spend more time on that. The sparse data tend to be slower, although there are different optimized libraries for that. And it's good to pick the model that really fits your for your data. These are some really common and easy formulas that you use with your dense data. This is the Euclidean. You see the Euclidean distance, the Gaussian kernel, the dot product. The dot product is nothing for, else just counting a similarity measure. It's just kind of like the Euclidean distance in a different sense. You can take your data, you can remove the mean, you can normalize the variance, you can do matrix multiplication. When you have sparse data, we can compute dot products. Dot products are more like joins in the database community. You cannot compute Euclidean distances. I mean, you can, but most of the times are meaningless. You can do matrix vector multiplication. You cannot do a mean normalization because you will blow up the memory. You can do variance normalization. Most of the times you cannot do matrix multiplication, and you tend to use mostly linear models. If anybody wants more explanation about that, we can take it offline, or you can ask a question right now, but I'm not sure that these are going to be really interesting for you. Interesting for you. There's a kind of like question that whenever you use a zero, what does it mean in your data? So typically when you use, dense data over here, this zero over here means that, the grade was zero. It doesn't mean that he didn't take the test. It meant that he scored zero. He didn't answer any question. Well, this could be a different case, for example, when you go to other types of data. Like in the user movie or user product, this zero means that he hasn't really purchased the product, or he hasn't really seen the movie. It doesn't necessarily mean that he saw the movie and he gave a score 0. No. Actually, in this particular case, that's why they avoided having a 0 rating. They had from 1 to 5, so that they can use 0 as the default value if you haven't seen it. This actually means that these are things that I don't know, and this is something you have to focus that you can give an answer. Like, can this user buy this product? Is it possible? So these are missing values and not real values. Do we understand that concept? I believe we do. Again, this is a different way to figure about sparse data as a graph. We talked about that before. There's something else called categorical data. Whenever you have a value, we talked about that a little bit before. red, blue, green, or brand would be Audi or Ford. Typically, the way that you represent this data is that you create, if you have three attributes, so basically here you have 1, 2, 3, 4 columns. This column that is continuous, we just keep it as it is. But as I said, machines don't understand about letters, they understand about numbers. Okay? So basically what I do is that I know how many different colors I have. So I have red, blue, green. So I create for every category an extra column. And here for the cars, I create one for Audi and one for Ford. And if it's a red, I put 1. If it's blue, I put 0. If it's green, I put 0. So this 0 is a completely different 0 over here. I don't want to get you confused, but I just wanted to say more about that with categorical data, because they're words, we convert them to numbers in that way. Don't make the mistake to say red as 1, blue as 2, and green as 3. If you do something like that, you've completely ruined your data set. Because the machine, when it says 1, 2, 3, it assumes that there is an order, that blue is bigger than red, and green is bigger than blue, which is not really the case of your data. Okay? It's a completely different thing. Well, that's kind of like an exception. In reality, if you have k categories, you use k minus 1. I think we're going to skip this about matrix factorizations. We're going to talk about that later. These are like more technical questions. Okay, let's go to the third part, which is always. I don't know if you feel like having a short break. We've already been talking for more than an hour. It's 1 hour and 20 minutes. If people are tired and want to take like a 1 or 2 minute break, I'm fine with it. I know that what I'm doing is completely against teaching principles, presentation of 2 hours. My mother, who's a high school teacher for 35 years, would kill me if I would tell her that I did something like that. So, do you think, do you want to take a small break, Rob?
Oh, just a minute break and then brought up again. You know what? And this way, chat with you.
Can you hear me? Can you get closer to
yeah,
I'll pick up.
I'll pick up. Yeah, why don't we take a 2-minute break, and then if anyone wants to chat with you with any questions, they can send you a question.
Yeah.
Okay.
Okay, you're feel free to send us the chat, and we can, or what? Yeah, I'm perfectly fine.
Okay.
So when we're ready back, just tell me, and I will, resume. It'll take this 2 minutes. Okay, are we ready to start again?
Yeah, I think we're set.
Oh, okay. Okay, so you sent that test. I didn't see the chat. Okay, we're set. Okay, so we're going to the last part of this presentation about algorithms. So I have a slide that says, 80% of machine learning. Unfortunately, there are too many algorithms, too little time, too many software libraries, too many databases, different databases. Chances are, most of the time, you will have to code an algorithm for the platform you work. No matter how many different platforms are out there or different libraries, there are not all possible combinations. So some of them run on Ubuntu, some of them are run on Linux, some of them are run on Windows, some of them are run on SQL Server, some others run on Hadoop, some others run on, HPCC. Unfortunately, there's kind of like a chaos like the one that existed 30 years ago with operating systems. Like you had before, ended up having 2 or 3 major ones. We have separate smaller ones, and that was a problem. And the good news is that there's about 10 algorithms that they account for 80% of most common cases. So we're going to talk about them. And learning them, it's not very easy, but it's always better to learn 10 than 10,000. Okay? And since you're not really the people that are going to do the coding, there is some value understanding them. Because first of all, you will know if the people talking about, you hire somebody to do something, you explain a strategy, it's always good to know what he's trying to do, to find out if he's at least or she's at least on the right path, knows what she or he is doing. So let's see another taxonomy of machine learning. I presented, so far supervised, unsupervised, generative, discriminative, behavioral, content-based. This has to do more with the data, less with machine learning. But there's another one called interpretable versus non-interpretable algorithms. In general, I'll give you some examples. So linear regression, linear support vector machines, decision trees, Bayesian networks. These are interpretable models. And non-interpretable are nearest neighbor support vector machines, the non-linear ones. Non-linear regression, deep belief networks. What do I mean by interpretable and non-interpretable? So there are methods that they will answer the question yes or no, A or B, black or white, 1 or 2, like a classifier. They will give you very good performance. They will be, 99% very accurate, so they will make correct predictions. But they are not going to give you an answer to the question, what are the features or the factors that actually contribute the most in your decision? Okay? So, in principle, if you are looking for performance, you tend to use methods that are non-interpretable, and typically they give you better performance. Not that there cannot be the other way around. But if it's very critical for your operations to know what is behind the scenes, like is it the specific day that my product sells more? Is it because of the weather? Is it the weather the most important factor? Is it where I put the product? Is it the gender of the buyer? If that is very important for you, then you should switch to interpretable models. And interpretability, some people, associate that with causality. What is causing the result? What is the cause of the result? Personally, I'm not a big fan of interpretable models and confidence intervals and all these things because it's kind of hard to trust them. For those of you that have taken a linear regression course, you know that sometimes linear regression, you can't really you can't really rely on the confidence or the significance scores. It can give you completely twisted view of the world. I'm trying to remember this example with miniskirts affecting the sales of ice creams or something like that. But it turns out because miniskirts are associated with the weather, but you only observe miniskirts. By observing miniskirts, implicitly you observe the weather. So making the association that miniskirts increase the ice cream sales, it's a wrong assumption. This is basically because when the weather is good, people also wear miniskirts or will wear miniskirts. But if you can come up with a good theory based on your machine learning model, that is very important because you can design your future, okay? So if you know, so far the models that I have described are kind of like observable. Based on this reality, answer a question yes or no. But if I ask you a question, what would happen if I change this parameter? Like, you are passively collecting your data, but you are not actively. Like when you're doing that actively, then you need to have a theory behind that. Like, which parameters should I tweak in order to increase my sales? Shall I have a promotion on Christmas Day, before Christmas Day, after Christmas Day, and things like that. Now, let's go into the methods one by one. The first one, as we already started talking about, is linear regression. It's kind of the queen of machine learning. It has been there for several years. People might ask, well, isn't that a statistical method? Why are you talking, why are you calling that machine learning? And I will grab this opportunity to explain the difference between statisticians and data scientists or machine learning people. So somebody said that machine learning is the name of statistics in Silicon Valley. Okay. Obviously, these two things are very close together. They're related. Machine learning people use a lot of statistical, old-fashioned statistical methods. All the new methods that they have invented have their roots on old statistical methods. I think the subtle difference is that machine learning is based on, let's put it that way. Statisticians were based on small data volumes, based on some very strong assumptions about the quality of the data. They typically work with very clean data, and they had some intervention or participation on the collection process. For example, people do their clinical trials. They collect data very carefully under controlled environment, and psychologists, they design their surveys the way they want. They have a small population. Now, machine learning has the aspect of, a lot of noisy data, and my algorithms are not always that complicated or complex. I actually have to have more data and simpler algorithms. In reality, this is going to give me a better result. This is the paradigm that Google kind of created and brought into the modern technological world about 10 years ago, that you don't really need complex algorithms. You need a lot of noisy data, computational power, like Hadoop, HPC systems. Google was one of the first companies to have these huge data centers. Okay, so this is a big difference. For example, a statistician, in order to use linear regression, first of all, he will have to validate that there is heteroscedasticity in the data. They are Gaussian. All the assumptions that linear regression. The machine learning person or the data scientist is more like a hacker. He will take it, put the data in, kind of like ignore the assumption, test if it works or not. If it works, we'll keep it. If it doesn't work, he's not going to look into the details. Also, in machine learning, people tend to use methods that they are what we call distribution free, which means that they don't really give you the best results, but they work well with all types of data. Okay, and we're going to see some examples about that. So on the left, you see the traditional two-dimensional regression problem where you have data and you're trying to fit a line, and it's a pretty good fit. Your data really are on a line, and this is the formula you are using. You call the betas are the factors or the regressors, and then you come up with values of beta and confidence intervals, so how far away can they deviate, how significant they are. Okay, so this is, as you can also see here, an interpretable model, because if beta value is very high, you can say that X1 factor has a big impact on the result. And of course, for every beta you come up with significance, means how sure you are this beta is really 10. And then what's the confidence interval? It's like between -10 -1 or 10 +1. Now, the reason why I put this example over here is because this data, this type of data is not really linear. Okay, there is something we call the trend. Okay, so there is a linear trend. The data is going down, kind of like the average of this signal is going down. But the data and so on has like variations around this line. Okay, and the reason why it is everywhere, because sometimes with machine learning, we're not really trying to model the data exactly, but we're trying to model just an aspect of it. And here the aspect is, the trend. I think this is the market value of Citigroup, but it could be anything else, where on a short-term basis it's very difficult to predict because it really varies too much. But on a longer term, and that's what you're interested in, there is a decline. Okay, there's a negative trend. And that can be very useful for the type of problem you're working on. And then this is another example over here. This is actually, okay. There's something we call polynomial regression, where your data doesn't really fit on a straight line, but you need a polynomial curve to model it. And this is, a case where your data are not really on a line at all. Okay, so linear regression can fail. So linear regression is kind of the first thing you try, and there are several tricks to make it work. One of the things you have to consider when you do linear regression is kind of like model selection, and which means that you start with all the features, and then you realize that you don't need all of them. You have to somehow, most of the time, so you start with, let's say, 500 regressors. Like here you see we have only n, and n can be pretty high. There is a problem if two regressors are correlated. Okay, so if you put as an input your education and your income, then that might cause a problem, especially if they're linearly correlated. So if we know, for example, that if you go to Harvard, you are more than 100. If you go to Georgia Tech, you are between at $80,000. So if there is like a straight correlation between them, that can make your model fail. So we have something that we call model selection. Okay, you might have heard that as stepwise regression, forward, backward, lasso. These are different names. And we're going to see later when I talk about regularization why this is important. In general, if there's a strong correlation and you don't remove it by picking the coefficients, your model is going to crash. Okay? So you need to account for that. Are there any questions about regression? We probably have to hurry up because we're running out of time. Sorry. Now, regression, as we said, is something that's trying to predict continuous values, like the volume of data. If your data has categories, then we use something we call logistic regression. So it's this formula down here that probably doesn't really tell you anything. So basically, it's like regression. So this is, A plus, I'm going to mark it here. A plus B1 x1 plus B2 x2. This goes in here. And if you remember before, that was y in the previous example. Now we take this y and we put it in this too complicated formula, and this formula is also called the sigmoid function. Okay. Now what happens is that logistic regression is great for classification. So you see, for example, in this particular case, it's able to draw this line over here and this line over there to separate the crosses from cycles. Another way to see logistic regression is like as a neural network. It's a single layer neural network. And logistic regression is used heavily for click analysis or for advertising. So basically you have a user that has clicked this specific advertisement. What is the probability of clicking a new one? Okay? It's a very, very, very common model for ad clicking. And what is really important to see is that, logistic regression is able to draw these complicated lines. If I was trying to separate crosses from cycles with just a straight line, that wouldn't be possible. Wherever I would draw the line, I would leave some, I would introduce some errors. So logistic regression is able to separate classes that they kind of like interleave, is one after the other. So if as well I have x's over here, it will still be able to draw that line and separate it. What it couldn't really do if I had a case like that. So if I had so whenever we have classes that it's one inside the other, it wouldn't really be able to draw that line. Okay, so it has some restriction. But most of the times it's one of the most popular tools that works pretty well. Any questions on that? I would appreciate if you tell me that it's too technical, less technical, we get the main idea, we don't get the main idea. Any feedback would really, really be helpful for that. Because it's kind of like a hacky way of explaining methods. It's a lot of them and we can't really go in depth. Now, what does this mean? Be an ecologist, love trees. Let's talk by example. Decision tree. Okay, so we're trying to decide whether a game is going to happen or not. Play or don't play. Okay, so y is the variable. Oh, sorry. Y is the variable we're trying to predict, and it can be either 0 or 1. 0 is play, 1 is don't play, not play. Okay. And we test the outlook. And then the humidity, and then the wind. So basically this is a decision tree. Consider we've built it. So when we start, we have 14 different types of instances. So this is our training data, okay? So there's 14 days that we have to play this game. And so it means that we have 14 points. And each point has, three different attributes. Was it sunny, overcast, or rain that day? Was it humidity was more or less or more than 70? And was it windy or not? So every point has three attributes over here. So we had 9 instances where we played the game, 9 days that we played the game, and 5 days we didn't play the game. So if we just ask a question, what is the outlook? The days that it was sunny, there were only 5 days that it was sunny. 2 out of 5 days we played games, 3 out of 5 days we didn't play. If it was overcast, there were only 4 days with overcast and all of them we played. If it was rainy, 3 days we played, 2 days we didn't play. So if you see, now that we have a new day, if we know that it's overcast, according to our training data, we don't really have to ask any question. If it's overcast, yes, we're going to play it again. Now, if it's sunny, we don't know. Chances are like 40% we're going to play, 60% we're not going to play. So we have to ask another question. Is the humidity over 70 or less than 70? If the humidity is less than 70, yeah, we play the game. If it's more than 70, we didn't play. The day that it was raining, if it was windy, we didn't play. If it was, not windy, we played. So basically the decision tree, what it does, in short, is takes your data and starts like trying to ask questions that if you ask them, they're going to give you, a pretty good answer, a very decisive answer. So, for example, if our first question is that, is the humidity less than 70? First of all, we don't know what the humidity was the other days, but it doesn't matter because the reason why you don't really ask this question because, if the humidity was over 70 and it was sunny, we know that we can play. And that we're not going to play. Now, if the humidity is over 70 when it was rainy, which obviously would be the humidity that day, we could play or we could not play. So asking this question first doesn't make sense. Decision tree will figure out what questions you should ask first, and what you should ask second and later. Or the question that you should ask before than others. Like when you go to doctors love decision trees because they're trying to find out whether you're going to have cancer, and by asking you what your blood pressure is, it's not going to give them an answer. First of all, they're going to ask you what was the specific blood result, because they know that if you do this test, 80% of the people are going to have cancer, 20% they're not going to have. So it's very indicative. Immediately they can reduce their set into something that is more decisive. Now, kind of like the same idea applies for regression, where you're not really trying to, and unfortunately we don't have enough time to get into that, but here we were getting discrete answers, like are we going to play the game or not. Now, if what we're trying to predict, for example, is again sales volume or something continuous, here you wouldn't really measure. Here we say we play, 40% of the time we didn't play, 60% of the time we didn't play. In regression trees, you will say 40% of the time, 40% of the data points have the same predicted value. So if it was just like a supermarket or we're running a decision tree, or we call it regression tree, so for example, all the data points that are grouped together, they have very, very similar, sorry, I need to use that. So all these points that are grouped together, they have, the similar values around 40. All these points over here, they have a value around 55. Anyway, I don't want to get into the details. If you understand the decision tree is pretty much enough. I know you're also tired right now, so just remember that decision tree is for classification, regression tree is for prediction. And the advantage of that, again, just to mention that decision trees, regression trees, you don't have to make any assumption about your data being Gaussian, zero mean, and all these things. They work with any types of data, one of the methods that data scientists love. The naive Bayes classifier that Robert asked me to explain, let me give you an idea. If you have a coin, whether you're gonna, and you toss it, if it's gonna be tail and head are two completely independent events. So we represent them as two independent, entities. But when we talk about like rain, you know that rain is actually conditioned under the cloud formation. Okay, kind of like the decision tree. If you have cloud formation, you're going to have rain. So the cloud formation and rain are like two entities that they are conditioned, like depend on each other. Okay, and let's get quickly into an example about spam. So, sorry if I'm a little bit inappropriate, but spam is inappropriate. But I'm mentioning spam because this is the most successful use of knife-based classifier. So we know that if you see this word in your in an email, chances are that it can be a spam. So these are the set of words that are spam, and this is the set of documents, if you will, that contain the word penis. So you see that there's a big intersection, meaning that if this word is contained, it can be spam. So let's try to avoid math a little bit over here. So basically what this symbol says over here, actually let's use a different color, so that the probability of an email being spam, given the fact that it has a specific word, is the probability that we've seen this word on spam times the probability of having a spam times the probability of this word. And let me explain that in simple terms. So we have, let's say that we've seen 30 emails that were spam. Okay? 20 times out of these 30 times it contained the specific word penis. Now, if we have received 74 emails, 30 of them were spam. So basically we're saying that how many, out of 30, so that actually says that 66% of the time that we see a spam email, it contains the word penis. And then this is around like 40% of our email is spam. And this is the probability of seeing this word. So in 74 emails that we got, that we got, 51 did have the specific word. So we take this formula and it says that if your email contains this word, it's 40% possible that it's spam. Okay? Now, if you also add the word Viagra, you see that this probability goes up. Okay, again, you remove the sentence. You say, out of 30 emails, 24, out of 30 are labeled spam emails, 24% of them have the word penis. 20 of them have the word Viagra. So, and then, half of my emails almost were spam. So basically you take these probabilities and you keep multiplying them. So what happened over here is that we know that the probability of, being a spam when we have the word penis is, really 40%. It's small. But if I keep adding, Viagra, and I don't know what other words, this probability goes up. So, again, the knife-based classifier is a generative model, and you can also use it in text classification, where basically what you do is that for a specific category, you're doing just some counting. You say, okay, out of 100 times that I saw this category, how many times did I also see this particular word, this particular word, and this particular word? It's really, really very simple. It's one of the simplest and the most successful methods. If you want me to repeat it, I can. You can go through the slides, but I think it's pretty simple. You just, keep conditioning. You keep adding. So, for example, if there was like if I put the word decision tree over here, the word, okay, not decision tree, or machine learning, this probability will go to 0. Because we've never really seen the word decision tree in any spam email. So the probability of decision tree on a spam will be 0. Okay? So that's why you only contain words that you've seen before, and you kind of like see how often or how frequently they are over there. Are you happy with the explanation, Rob? You want me to explain it? You get the idea, okay? Okay. Let's move forward then. K-means is again clustering techniques. Basically, you have data and you want to put them together. So K-means what it's going to do, it's going to start with, so K-means is a way of like summarizing documents or summarizing, data. Basically, it means that if you have, if for some particular reason you have a set of customers that have a particular combination of age, gender, and location. So you can imagine, for example, that here you have, customer with specific age and weight. You can put here age and weight. You can see that you have 3 different types, one here, one there, one there. And basically, the center of that gives you that's kind of like the most representative customer. Like in this particular cluster, the most typical customer would be the one that is, 150 pounds and 53 years old, I'm just saying. Now, the way that the algorithm works is really simple. It just starts with some, initial centroids. Each point gets assigned to the closest centroid. Maybe this one will go there. Then the centroids get recomputed iteratively. Again, we don't really have that much time to get into the algorithms. So the centroids will, might start from here and will keep moving towards there. This will actually, no, this will probably move towards here. This will move towards the center over there. Now, well, let me see. I'm going to talk about singular value decomposition very quickly. It's probably one of the most successful and traditional methods in machine learning. You can think about it as a clustering method. Okay, so we need to wrap it up. It's getting 3 o'clock. So I'll just go fast. Basically, it just takes a matrix. And it decomposes to smaller matrices, and basically, this can be the user movie matrix, and this is something that describes the users and something that describes the movies. These things can be used later on to make recommendations. We're pretty behind the schedule, so anyway, let me move faster. Pictorially, for those of you, you're taking something that is very big, you're breaking something to smaller, you're summarizing things. Again, its row of A matrix can be images. Then when you do the decomposition, it will find the most relevant features of the images, and it will just throw any noise on the side. Again, it will take user and movies, and it will find movie profiles or user profiles. So that would basically tell that this specific user, user over here has this kind of like mix of movies. So kind of like groups movies together that, Star Wars and Star Trek and Back to the Future is a typical, sequence of movies works together. And this would be, a specific category of users that they watch, all the users that have values along this dimension, like sci-fi, kids movies or different things. It's the basic method for collaborative filtering, as I said, user products, the one that was used is used very extensively in the recommendation systems. Again, graphs, this can be a social network over here. Social network, proteins, text that it has been decomposed on dependencies between letters, again, this one is, the social network around the senators. Now, what we do with graphs, it's like a big chunk of machine learning. One of the things we do is compute page rank. I really wanted to, maybe, let me see. Okay, so I will just talk about that and then we'll close it because it's really important, like the last algorithm. So everybody is familiar with PageRank. You know that this is the way that Google computes the rank between web pages. And I'll just give an example of how it works. So basically, if at Commerce you have this, you have a million candidates that you wanted to kind of like find who is the most important so you can place him. And the only information you had was the endorsements, the references. What would you do? Would you just pick the guy that has most of the references? That's kind of a solution, but not very optimal, because if I put on my resume 1,000 references from the Giants of Atlanta, I wouldn't be as important or as valuable from the guy that has 2 endorsements from a Nobelist, from 2 Nobelists. Okay? So that's exactly what people do in the early stages of the web. They would just count how many backlinks that each web page has. But that was very easily available by hackers. So the hackers will create a sea of fake web pages pointing to the, to their malicious or bad web pages, and then search engines would think that these are important. Now, then you would say, okay, so you have to figure out who is endorsing you. Now, even if I have endorsements by 2 Nobelists, and you realize that one of the Nobelists or these Nobelists have endorsed another 1 million people, you wouldn't really count their opinion that much. So basically, in order to find, my rank, my reputation, what you really need is to find out what's the reputation of the guy endorsing me, and how many other people this guy has endorsed. So this yellow guy over here, is pretty big because there is a lot of people endorsing him, but these people, because he's endorsed by blue, he's important, but blue is also endorsed by, a lot of other people, and these people are endorsed by other people. So this is kind of like a closed environment. It's a closed cycle. And what happens is that at the beginning you assign reputations, and these reputations are passed to the people that you point to, and these people are pointed back, and it's kind of like something like a random walk. It's already 3:10. I don't have much to explain about it, but if you see the example over here, this guy has a page rank 100. This guy has a page rank 100, and he splits his reputation into 2 and gives 50 to this guy, 50 to the other guy. Over here, this has 9. And this is split across 3 links, so this guy gets 53. So possibly at some point, through several hops, this goes back over here, and, it's also split around the network. And it turns out that this process, you start with some, random values, and you start like spreading or giving your reputation to other people. This reputation eventually comes back to you in one way or another, and it turns out that the ones that gather the most are the most important people. This is a case and kind of like an exception where if the network was small and they have like this feedback loop, it will make the reputation go to infinity. We don't have really these cases in social networks, and if we have, we remove them. But this is kind of one of the most common algorithm in graphs. It's associated with a random walk. Again, you start with something. This one is passed over to your neighbors, and when you start from here, this is passed to here. Probably there's more links goes to there. Moves randomly. It's a random surfer model. Let me give you an example. If you were just taking a car and you were driving from city to city following the roads, and then you were counting how many times you passed through these cities, you will realize that most of the time you went through New York and Atlanta and San Francisco. Why? Because there are many roads, taking you there rather than to, Macon, Georgia. That's exactly what it is. You do random walks on the graph, and you count how many times you crossed a specific city. Cities that they are important are going to be visited most. Okay. So with that, I will kind of finish the presentation. So there's a last slide about splitting graphs into communities. Finding cliques and communities inside graphs. Another important thing. I can explain more. Again, you can do that with a diffusion. If I assign, a value over here, this will go here, then it will go there, it will go back here, it will go back there, and a small thing will link over here. So after we run this game of random walks, eventually this will become very blue, and maybe this and light blue over there. So eventually we know that this is a community, and then if we repeat the same experiment, over here, put the red somewhere here, it will get diffused. We'll go back here, go back there. A small thing will link over there, and eventually we'll be able to say that this is another community. Again, on graphs, you do random walks, you can get reputation, and you can also get, detect communities. So, I don't know if people want to ask any questions, want to give feedback. We are, 12 minutes over our time. Of course, we started a little bit late, so I think we're just 6 minutes. And if we count the break, we're just in time. So, I would really like people to ask any questions if they can, if they have, or give any feedback. Rob?
Can we get copies of the slides?
Yeah, actually, in the very first, it's under Google, Docs, and the very first link that I put on let me post it again, on the chat, has the link.
Okay. You
can download it. Let me put it again for people that join.
Oh, I see it. Okay.
Okay, now I put it back. So, it would really help to get some feedback for people. Again, I wasn't really very sure about the audience, the level of, relevance to the subject. So I hope I didn't bore you or didn't waste your time.
Yeah, no, thanks for doing it, and I think everybody on the on the call appreciated it.
Okay, maybe you can send me an email or have a call later to discuss it. Okay, so if there's nothing else, then we should, and I'm also recording it, so if you want to put it, online, put it on YouTube or something, you can also do that.
Cool. Thanks again, Nick.
Okay, thank you again also for your attendance. Hopefully we will have a follow-up on that.
Yep.
Bye-bye.
Okay, bye.
Bye-bye. Okay.